Hello, welcome to my presentation. This is the work that we have presented at the AIROS conference. I am Gonzalo Ferrer, and I will talk about the robot companion task that we have developed at the Institute of Robótica Industrial in Barcelona. So first of all, what is the motivation? Why do we need to company people? Well, we will define company not just as a simple follower, but as a more intelligent way to follow people. So for instance, here we are trying to accompany this person, and we want to be aware of prediction information regarding its destination, and we also want to react according to the environment, that is, other persons in the environment and static obstacles. So the overview of this work, here I will briefly talk about the perception block. We have mainly used laser information and a feature-based people detector. Here in the social awareness navigation framework is where we have done mainly our contributions. First of all, we have extended the social force model. We'll talk about later about the social force model. Then we have proposed a human-aware navigation using this extended model and human motion prediction. We require somehow to learn the parameters of this system, so we use some volunteers in a real experiment to get those parameters. And finally, we have proposed a novel metric to evaluate the performance of this companion task. Briefly, the social force model introduced by Helbing is a model that treats people as two-dimensional particles in a space, and they react accordingly to external forces. In this case, we have a steering force to a destination in blue and interaction forces with the environment. And the red one represents the person-on-person interactions, but there are other kinds of interactions like an obstacle-person interaction and a robot-person interaction in this case. This is where we have proposed the extended version of this social force model. So the summation of all the forces would be the steering force plus the interaction forces. As I said before, we require some parameters to get these interaction forces. Each kind of interaction has its own parameters, and we need to obtain the parameters for the interaction forces between the person and the robot. So how do we obtain these parameters? We have made real experimentations with people. They were told to naturally walk to a destination, and the robot was in the ascent. So we recorded the trajectories, and we have minimized the error between the observed position of the person and the expected position, applying these forces with these parameters. So the minimization of this summation gives the parameters of the person-robot interaction. As you can see, there's a height variability in the values of these parameters, and it is natural since people react differently to the robot, different persons. So there's another element in the social force model, the anisotropy element. It's a function of lambda, and it represents the fact that frontal forces are more significant than back forces. So this gives an idea of this concept. Well, how can we make use of this social force model to navigate the robot? Well, we treat the robot as a two-dimensional particle, same as a person, and we will use these forces to make the robot navigate the environment. So first of all, as I said, we are accompanying people. We don't have any information regarding our destination in the environment, so we need to somehow infer it. So we are using an algorithm described in this publication that tries to get the best expected destination of our target person. Additionally, we have a second steering force that tries to get to the target person, and that's normal since we are trying to accompany someone, not get to their destination. The other interaction forces would be the same as described before. We are reactive to obstacles and other persons. And the summation of all these forces is the resultant force. As we said before, we are summing all those forces, but we require in this case some weights to measure especially the contribution of each of the steering forces, and since we have now two different steering forces. So how can we obtain these steering forces? Again, we made some real experiments with some volunteers. They were given a Wii remote controller, and they were trying to get to a destination in a real environment while the robot was accompanying them. So they were told to hit the plus button every time they felt that the robot had to pay more attention to their destination, and the minus button every time they felt that the robot had to pay more attention to them to get to them. So by doing this, we sum the numbers of plus and minus, and we map it with a logarithmic function to obtain the beta and the gamma parameters. There's a function of the evolution of these parameters during this experiment. Another contribution of this work is the quantitative metrics. Typically this was done using some interviews and other methods, but not a quantitative expression that measures the performance of the accompanying or the following task. So to do this, we have made use of the proxemics theory, and we have defined three regions: an external A region, and a circle centered at the robot, the B region, which is the best area that we want the robot to stay while accompanying someone, and the C region, which is the personal space of the person. We don't want to invade this region. So the performance is done interacting the section of the robot and these areas, and we obtain a function from 0 to 1 measuring the performance of the accompanying task. And here there's two videos of our simulation environment. On the left hand, we can see an open space with no obstacles, and the robot tries to get to the target person, which is an orange cylinder, and meanwhile tries to avoid all the persons in the environment. And on the right hand of the slide, we can see the same. The robot tries to get to the orange cylinder, that is the target person, but there's obstacles in the environment. So these simulations were done with a high density of people that was done to prove that the algorithm worked with lots of people and few people. So here are the results of the simulation. We have compared our method in red in all the figures with two other methods. One is a social force model, but not using prediction information. That is, the robot does not try to get to the destination. It only reacts to the external forces. And the other is a proxemics-based approach, which only follows the person and is not reactive to anyone, just stops if there's someone inside. And we have measured this performance in a growing density of people in the environment. That is, on every iteration there were more and more people in this set. So as you can see, our algorithm outperforms the other, especially on more populated environments. And here in the right hand, this graphic measure the goal achieved, that is, if the robot was inside the region, the A region that was defined previously, when the person get to their final destination. So that is for the simulations. We now require some real results, real experimentation, and these are the robots that we have used. These are the TV and Dower robots as sequate platforms, and we have used laser information for detecting and navigating in these environments. That would be the Barcelona Robot Lab, urban-like environment, and this other one. So here are some pics of our real experiments, trying to follow some person, and at the same time we are trying to avoid all the obstacles in the ascent. As you can see here, there's an inferring of the best destination of the person while trying to accompany, and it tries to react to other persons in the environment, and when there are some changes in the destination, the robot needs to react accordingly. Well, there's also some limitations, especially in real environments, due to the perception. We have some problems like this one. We have lost the target, but we have manually reset this target in order to follow. So, as a conclusion, we have presented in this work an extended social force model for the robot and person interaction. We have proposed a human-aware navigation framework using this extension of the social force model. Then a multimodal interactive learning approach was used to get the best parameters of the resulting force that governs the robot behavior. And finally, we have proposed a quantitative measure of the performance of the accompany task. So that was all. Thank you for your attention.